This presentation will be a summary of a lecture that I did on introducing fractions and the terminology associated with them. We're going to start by looking at our basic model for talking about fractions, which is a unit square. Notice that the dimensions of the unit square are 1 by 1. That means that the area of this particular square is equal to length times width. It's equal to 1 square unit. And that's the basic model we're going to use for talking about the terminology on the next few pages. So let's go to the next slide at this point and take a look at some examples of how I can use this unit square to talk meaningfully about fractions. So we see that I have 3 unit squares that I've gone ahead and drawn. Let me go ahead and shade some parts of each of the unit squares. So I'm going to go ahead and do that in red. So I'm going to shade this piece here on the far left. I'm going to shade this piece on the left of the middle unit square and shade this left piece on the third unit square. Now, I can go ahead and come up with a notation that represents how much of the area is shaded for each unit square. Notice in the first unit square on the left, I have shaded one part, and the unit square is split into 2 equal sized parts. We call this the fraction 1/2. I can do the same thing for each of the other 2 unit squares. Notice I'm going to put a 1 in the numerator again to represent the number of pieces that are shaded, and 3 is the number of pieces that unit square is split into, and correspondingly on the far right I have a fraction that we call 1/4. All of these fractions where I have a 1 in the numerator, and the numerator, by the way, is the number that's at the top. I'm going to change the color to go ahead and write that. So this is called the numerator. And the number on the bottom of this notation is called the denominator. So the numerator is in the top and the denominator is on the bottom for this notation that I'm using. So anytime I have a 1 in the numerator and then a number, another number in the bottom, these kinds of fractions are called unit fractions, and they're the ones that have a 1 in the numerator. Okay, now that we've looked at unit fractions, we can also talk about multiples of these unit fractions. For example, the square on the far right, the unit square on the far right, if I had shaded 2 of those pieces, then I would have a fraction that is 2 unit fraction. It would be 2/4, which is 1/4 plus 1/4. So I can combine unit fractions to create any other kind of fraction that I want by just adding more pieces. Let's go to the next slide and talk a little bit about proper versus improper fractions. So first of all, notice that each unit square that I have drawn on the screen has been split into a certain number of equal sized pieces, and I'm going to call that n. In other words, n represents the number of equal sized pieces that I split the unit square into. When the number of shaded pieces is less than the number of equal sized pieces that the unit square has been split into, the resulting fraction is called a unit fraction, or excuse me, it's called a proper fraction. So let me go ahead and shade 2 pieces here. That represents the fraction 2/3. So I'm going to go ahead and write that here. That is a proper fraction, because the number of shaded pieces, 2, is less than the number of pieces we split that square into, which was 3. Notice that what that really means is that the numerator, and I'm going to abbreviate that, when the numerator is less than the value of the denominator, then we have a proper fraction. Okay, and in this case 2 was less than 3. Let's move over to the right and start talking a little bit about improper fractions. So in this case, for the unit square that I have up above, I'm going to shade both equal sized pieces that we split this into. And of course we can write the fraction for what we have just shaded in. There are 2 shaded pieces, and there were 2 pieces that we had split this up into. Let me move that down just a little bit. So this is 2/2. And this is an improper fraction because the number of shaded pieces, 2, is equal to the number of pieces that we had split the unit square into. So what we're saying is when the numerator is greater than or equal to the denominator, then we have an improper fraction. Let's look at one more example of an improper fraction. Let me change the color again to blue. I'm going to shade all of this particular unit square, so all three pieces, and then I'm going to shade one more piece here. And let me move the screen down a little bit so we can talk about this. So now, in this case, I have 4 shaded pieces out of 3 pieces that each unit square was split into. So this fraction, the shaded portion, represents a fraction of 4/3. However, we can also write this as 1 whole square plus 1/3 of another square. And normally we would write something like this in this form without the plus sign in between. This form is called a mixed number, and it's called mixed because we have a whole number piece and a fraction piece. So it's a mixed number where I'm adding a whole number and a fraction. Notice that this particular mixed number, 1 1/3, is equivalent. It's the same as the improper fraction 4/3. We're going to talk a little more about the relationship between improper fractions and mixed numbers later and how to go from one form to the other. But for now, the picture does the job of showing, in this case, why 4/3 is equal to 1/3, and that completes our talk about improper fractions. Let's move now to the next topic and talk a little bit about equivalent fractions. So what I'd like to do is go ahead and draw a vertical line that splits each of these unit squares in half. So each of these unit squares is being split in half. And the first unit square, we're going to go ahead and label that as 1/2 after I go ahead and shade in the part. And I'm going to go ahead and shade all of them in, just to show that they're all equal to 1/2. So this one is 1/2. And now I'm going to do something else here. For the second square up above, I'm going to come over here and draw another line that will split this square in half again. Now notice that that splits that square into 4 equal sized pieces, and I'm going to split this one using 2 horizontal lines so that it splits that square into 6 equal sized pieces. Now here's what we've got. The second unit square that's up above here, notice that there are 2 pieces that are shaded and there are 4 pieces total that the square was split into. However, notice that that is equivalent to 1/2, right? The same amount of area is still shaded in that case. And down below I have a fraction of 3/6, but again it is still equal to 1/2 because the amount of shaded area is still the same as it was in the original unit square that had the half shaded. So what we're noticing here is that by adding these extra cuts, if you will, I'm creating fractions equivalent to 1/2 but that have different numerators and denominator values. Now numerically, here's what happened. I doubled the number of shaded pieces here, and I doubled the number of pieces that the square was cut up into. So by multiplying the numerator and the denominator by the same value, which was 2 in this case, I created an equivalent fraction of 2/4. So 1/2 equals 2/4. And down below, numerically what we really did was I tripled the number of shaded pieces, and I tripled the number of pieces that the square was cut into. And so by doing that, I created a new fraction, an equivalent fraction, a fraction equal to the value of 1/2. So summarizing here, we know that 1/2 equals 2/4 equals 3/6. In fact, for any fraction, let's call this fraction a over b, where a and b are whole numbers. If I multiply the numerator and the denominator of that fraction by some constant whole number c, I create a new fraction that is equal to a over b by that process. Okay, so that's equivalent fractions, and that's how we can create them. We call this process building equivalent fractions because the numbers are increasing. I'm increasing the numerator and the denominator by the same multiple value. In the case that I showed, multiplying by 2 and multiplying by 3 created new equivalent fractions. Now, it doesn't take much to see that we can go the other direction. So let's come over here, and rather than using the pictures, suppose I have a fraction like this, 8/12. I notice that in this case, I could divide this by 4 and divide this by 4, and what this does is it creates a new fraction that is equivalent to the fraction that I started with. 8/12 is equal to 2/3 because I could take 2/3, multiply by 4 in the numerator and denominator, and create 8/12. So we know those fractions are equivalent. But notice what I've done. In this case, I've gone the other direction. I've taken the numerators and denominators, and I've made the values smaller by dividing out the factor of 4. Another way that I could have done this is like this. I could have had 8/12. I could have factored the numerator into its prime factors, which is 2 times 2 times 2, and 12 is 2 times 2 times 3. Now the advantage of factoring into prime factors is I can immediately see which factors in the numerator and the denominator will divide out. I can divide out a 2 here. That leaves a 1 and a 1 when I divide that out. And I divide out a 2 here and here. We call this canceling common factors, and it leaves behind 1 times 1 times 2 is 2. 1 times 1 times 3 is 3. And I can reduce that fraction 8/12 to 2/3 by going ahead and canceling common factors. Now the reason this might be a good way to do it rather than using the division method is seen with the following example. Suppose I now go ahead and take the following two fractions. Let's say I have 21/35. Now again, if I happen to look at it, I might notice that I could divide out a 7 and a 7, and I would then have 3/5 as my equivalent fraction. Now suppose I didn't see that 7 divided evenly into the numerator and denominator. Then I could again do what I did in the other example. I could take 21/35. I could break the numerator and denominator into its prime factors. That would be 3 times 7. This would be 5 times 7 for 35. And again, notice that now I easily see that these prime factors of 7 are common and can be canceled out. So 3 times 1 is 3. 5 times 1 is 5. And again, I get that 21/35 is equal to 3/5. And that concludes our look at some terminology related to fractions.